Okay, so these will be set of 3 lectures where we will try to go from very basics of fluids, some things that in your experience, for example, tornadoes, circulation, some general theorems of circulation and stuff like that, and which is to deal with ideal fluids, essentially. That means non-dissipative fluids without any viscosity, stuff like that. And then we'll slowly introduce the concept of viscosity, hopefully tomorrow. And then 3 is a very small set of lectures, cannot really talk about turbulence, that it turns out that any of these astrophysical systems interest in astrophysical fluids are very, very turbulent. And that basically changes a lot of conclusions that we can draw in the absence of viscosity. So it is small, but it completely changes the solution. I'll ask you to guess certain solutions and let's see. Then I have to quickly come to plasma physics. So the emphasis on this will be just on the macroscopic description. We'll be dealing with scales that are large compared to, for example, electrons, gyro radius and stuff like that. If you are resolving each electron and protons and stuff like that, then this becomes a completely different problem that requires a microscopic description of plasma, which is studied typically in terms of, say, Lasso equation, Fokker-Planck equation. But we will be dealing with macroscopic equations, yeah, which will require you to have some notion of continuum mechanics or continuum dynamics. So, can you define fluid? So because that these are only few impressions I can make. Okay? In 3 lectures, it's not possible to cover much of it. So these are set of references that you should look up. Yeah? If you are interested in topics in general on fluid dynamics. There are many textbooks, but this is just a sample few. 2 chapters on Feynman are very good. In fact, one highly recommended that you begin with chapters 40 and 41. It's called flow of dry water and flow of wet water. Yeah. So dry water and all, but it is characteristic Feynman. Is trying to tell you something already by the title of the chapter. Flow of dry water. That means basically ideal fluid that you can put that water on the surface, it will not wet the surface. So and then this is a very interesting textbook, HSN. All sorts of instabilities that are exciting, that and different kinds of waves. So have you worked out problems of sound waves in medium like this? Can you write down equation and derive from first principle the sound waves given thermodynamic conditions of this group? Yeah. How does one go about solving for these perturbed quantities like waves that we generate by speaking? Landau literature, of course, is very. This doesn't work. It's fine. So Landau literature, of course, is very good. Then for plasma, you could look up some. There is also a very interesting article by E.M. Purcell. It's a very nice article. You should read just on the role of viscosity in life. What low Reynolds number really means. That how by applying almost no force, you can actually move a whole ship. And why is it even possible? Concept of friction, dynamic friction, and all that. So, just to give some further impressions of astrophysical flows, you know that this is not necessarily astrophysical flows, but as you can see, the waterfall. Does this work usually? Yeah. Then I know what solve is. Maybe there is no battery or something. Or now it seems fine. Right. But if you try to solve system, which is like say even in this room, or water flow from a dam, and what sort of solution that emerges is one of the most challenging problems. It's an unsolved problem, turbulence, of course. Right? Where is the origin of such terms? That typically you are given a differential equation, yeah, most dynamic governed by, say, differential equation, you are set of any conditions. You can use standard techniques or to evolve and predict the future state. It is possible that the system becomes so nonlinear that the predictability is not even possible. You cannot predict the solutions at a later time, even if you start from a very well-known initial condition. Emergence of turbulence is one of the most challenging unsolved problems in physics, but it is celebrated unsolved problem in physics for centuries now. That is one thing that it is tough, but certain average behavior of fluids one can extract by certain techniques, modern techniques, which, if there is time, I will come to in the third lecture, that how some statistical properties can be extracted from a turbulent fluid, exact behavior of which is nearly impossible with any known technique, computer or hand, to actually study. All these systems, like all this nebula or interiors of the sun, this is a flow or a cartoon that the black hole taking material from a neighboring star. Material as falls on the black hole, forms an accretion disk. So, has some of these things been covered? How the accretion disk form and stuff like that? So, but anyway, this is all within the subject of fluid dynamics. Then why after all a thin pancake like this around the black hole, and then there are these jets. Motion of all of this is governed by the same equation. It turns out that a single equation is behind dynamics inside all these various astrophysical objects. So it is worthwhile spending some time to know what is a fluid. So can anyone define simply without looking at that now? So what do you think is a fluid? Huh? Something that flows, yeah, but then you can ask stars in a galaxy, yeah, they're also like flowing only. They're like in the galaxy, they're like rotating around a supermassive black hole. Is this fluid? Can I take the systems of stars in a galaxy as fluid? There are also large 10 to 13 stars in a galaxy. There are a large number of stars. What makes you think that the stars in a galaxy are not fluid and interstellar medium is a fluid? How do you decide? How do you judge whether something is a fluid and something is not? Interactive force. What is the interaction?
It's gas molecules that some of the between one molecule. But if we go to the stars and stuff, we find a lot of they get more into.
No, but how? I mean, then if there is a lot of interaction, it could also mean quantum. Is it quantum object? Are stars quantum objects? Okay, let's put it in some semi-controversial manner. Do we study these flows under quantum mechanics, or some very simplified Newtonian dynamics is enough to describe this? What do you think? Simple Newtonian works actually, and why it works, and when it breaks down. Unless you have a clear definition of the fluid, you will not even know when it breaks down and when you can apply and when you should abandon this. There are, of course, situations when you cannot apply this. Corona in the sun, corona outside the sun here, we know fluid description is expected to fail for the corona. Okay. But then why? The question is why?
And treat it as a question.
Why? What is the defining property of a country? When?
The scale of the system
Compared to?
The
stars in a galaxy are bounded to the galaxy. Interparticle separation is very small compared to the galaxy size. Mean free path is the correct thing. That the fundamental property to define continuum is collisions. That they should be colliding very frequently, so that in a small enough unit element, for which you will write an equation of motion. You're writing an equation of motion for what? That is the question one has to ask. So when you're writing a simple Newton's law of motion, you're looking at a single particle subjected to variety of forces, and for each of those particles, you will write equations of motion and solve it. In principle, this is a doable thing, but you know that number of particles in this room You can work it out, right? Avogadro's number, yeah. Number of particles are huge. For each particle, you have to write these three equations, right? For each component of the velocity. So, number of equations that you must solve to simply understand a simple problem of air current in this room, or as we speak, sound waves in this room. You will be forced, if you adopt to the particle approach, you will be solving more than 10 to the 40 equations just for looking at a simple problem. So one has to simplify the description. This is the reduced description in which you lose some information, yeah, but you define some sort of an average fluid particle, what is called a fluid particle. You define a new particle. But now that fluid particle becomes your unit element, and your resolution is not supposed to go below that scale, meaning you are blind to scales below that. You can only resolve at the most this unit particle for which you write the equations of motion. So instead of writing for each individual particles, you define some sort of a bag of particles which is all moving. I mean, boundaries of these particles, they are all moving. It's a fluid, they are free to go. Another property of fluid is that it cannot sustain a shear stress. If I apply a shear on a fluid, it moves, it yields to the shear stress. Right? It cannot sustain a shear. Unlike solids, where I can put my hand here and the shear stress can be supported by forces and interactions within the solid. With fluid, it will not happen. You put shear stress on the fluid, right? So this is another property. So this can deform a small, this is a single unit cell. By unit cell, you know that this is the smallest unit of your problem. Okay. So there will be particles. It is made up of particles only. These are, say, the gaseous particles in this room. I can think of small enough parcel, which is very tiny, as a fluid particle, which has, say, just for the sake of it, 10 to the 26 particles for, say, the Avogadro number of particles within a unit cell, and you are no more bothering about writing equations of motion for each of those individual particles. The only way this notion of fluid particle makes sense is when the number of particles is nearly preserved in this unit cell. Yeah, it should be nearly preserved. Otherwise, now at one instant t equal to 0, you have so many particles, and next instant this deformed and you had only 2 particles because the particles were just diffused out of that unit cell. Right? It is possible. So the idea of fluid particle or unit cell makes sense if there are very frequent collisions, so that the particle at the near surface, whenever it tries to escape that fluid particle, imaginary surface, imaginary fluid particle, it collides another particles and tries to come back. Okay, so that the collisions are very frequent, and whatever is your notion of unit cell in a fluid, it retains its identity in terms of number of particles. So it is never a case that suddenly you have a fluid particle at this distance and next it's a vacuum and there is no particle there. That will happen to stars in a galaxy. If you work out a mean free path, is larger than the size of the galaxy, although the interparticle separation is very small. So it depends on the system you talk. So let's just define formally. Of course, if the particles are too densely packed, okay, then the quantum interactions will become important. That happens in the interiors of the star, neutron stars and white dwarfs, in which case you cannot treat the fluid as classical. Right now we are talking of classical fluids, and you can work out the numbers, whether the star or normal matter in a star or the sun, whether it is within the classical limit or not, that you can work out. It's a very simple calculation. You work out at the Broglie wavelength. At a given temperature, you know the momentum of particles, you can work out the Broglie wavelength, lambda equal h by p. Yeah. If that number is much smaller, each particle, I can draw each particle, there is never a single particle, there is always some sort of a smearing around a particle, right? So if this is your particle, and if there is another particle which is within the Broglie wavelength of other particle, you would say that the quantum overlap is now significant and the quantum effects must play a role. Okay. Then of course you cannot treat the place classical and you must do something else. That is what is done for, say, superfluids in neutron stars. Neutron stars, it's an example of having superfluids in the interior. And that also is a very interesting dynamics. Turbulence there is quantum turbulence. Yeah. So, but if the particles are far away, so that interparticle separation, if small n is the number density of particle in a given volume, yeah, you can convince yourself that n to the minus 1/3 is the interparticle separation, right? I can write it as A, interparticle separation, right? So that is obvious to you, right? So the interparticle separation should be much larger than the Broglie wavelength so that you ignore the quantum effects. It should be still much smaller. The interparticle separation, like here, should be much smaller than this unit cell in consideration. Okay? So that you can even define something called a unit cell. Okay? But this whole interparticle separation will still not make sense if the corresponding mean free path, which is an average distance a particle travels before colliding or hitting another particle, okay, in the medium. Okay. So if the mean, suppose your densities are such that your unit cell of dimension delta x satisfies this criteria. This is the case with stars and galaxies, by the way. That your delta x is indeed much larger than the interparticle separation. But if the mean free path is comparable or larger than this delta x, next instant these particles will travel a distance of lambda in any direction here, which is larger than the unit cell, and the identity of the unit cell cannot be preserved. So the very defining property is that this mean free path must be much smaller than the typical size of a unit cell. Unit cell is the limit of resolution of the system, and this unit cell must be much smaller than the system size. If all these inequalities are satisfied, only then there is a sense, or you could say that there is a notion of fluid. If any of these breaks down, you are no longer in the regime of fluids, and you must do something else to study the dynamics in the medium. Corona in the stars or the sun, that's one example where it is the dynamics largely collisionless. So the defining property is collisions, frequent collisions such that your mean free path remains small and defined. So this is quite an important point. That's why I'm stressing so much. But we can. So within this we will talk. This is a continuum mechanism.
I think defining the unit cell ourselves, so can't we just define it in a way that all those things are satisfied? We take it to be so big that it's bigger than the interparticle separation, but smaller than the
Yeah, but suppose your system is this big. The mean free path comes with its own definition. Now you work out your cross section. This is n is a number density. Number density for a system is given to you, right? None of these numbers you can choose arbitrarily, right? So it will matter if I take my number density. So just take the example of this room. You can work it out. Sigma is typically what? It's more like a Bohr radius. Only when the particles collide with each other they interact. If you say, you can take some order unity factor of the area offered by a molecule as the cross section. Cross section is probability of collision, right? So probability of collision is typically that what is the area that a molecule offers in a given environment. That of course naturally depends also on the number density, how frequent the collision should happen. So put together dimensionally. So this is 1 over n sigma. Now sigma, if you take hydrogen atom for example, you can try to work it out of molecules in this room. Take the number density of thing in the room. If suppose it so happened that the number turned out to be 10 meters, suppose. That is not in your control. Suppose the number turned out to be 10 meters, you would not be able to apply fluid description to study anything in this room. You understand? Because you can then define a fluid at a much larger scale. That may be true. That is what you are saying. That can I go to a regime or scales where this is always satisfied? Yes, but that may not be your system of interest. You understand? Suppose I'm just interested in wave propagation in this room, and mean free path turned out to be, this is what will happen. Suppose you try to work out a sound wave in corona. So it's a valid question. Sound wave in this room, or sound wave in corona, or somewhere in star. You have to work out a setting, different setting. You may have to first see whether you can do the continuum dynamics or not for that system. In fact, I should have given a number for the stars in a galaxy. You will find that this galaxy is how much? The diameter of a galaxy is about 20 kiloparsec. If you work out the mean free path for stars in a galaxy, it is more than 20 kiloparsec. So clearly, we cannot treat them as a collisional bodies. They are colliding. But now it turns out for this room, it is 10 to the minus 5 centimeter, which is very tiny. Right? 10 to the minus 5 centimeter is very, very tiny. So I can always push an air here, or while we speak, they are pushing an air here, and they are pushing further molecules, and that's how the waves are propagating. How exactly? That's a calculation to be done. But at least the description seems possible. And given that the sizes are so small. For the interstellar medium, if you work out the same number, these are the typical number densities, you get the number which is 10 to the minus 5 parsec, which is a very large scale, but not for the size of the ice. ISM is huge, right? So again, I can take an entire galaxy. It's like, suppose this is a galaxy with a spiral arm, right? And in between, you have this interstellar medium. The size of this is 20 kiloparsec. I can always pick a unit cell of size 1 parsec, yeah, which is still 5 orders of magnitude larger than the mean free path. So for gas in ISM, I can still apply my usual continuum dynamics. So this is the most important number to first calculate to see if you can even treat this as a continuum or not, despite the size of the system. Now the derivatives, you will be, let's look at the origin of nonlinearity. In fact, what is the origin of that celebrated turbulence problem? Where does it come from? Actually, the origin is very simple. Yeah? Whenever we write typically a derivative, what do you do? To define a derivative of a quantity, you take a quantity at here, take a quantity here in space, I'm saying. Yeah, you take quantity at 2 neighboring points, yeah, and take in the limit of infinitesimal separation. Yeah, what is the change in the quantity over that distance? There is a derivative, right? But now in fluid, because you know that it cannot sustain any shear stress, whenever there are forces in the system or stresses in the system, fluid flows, right? And the quantity changes. One important thing I did, sorry for that. So having defined a unit cell, what are the quantities of interest for which we will write the equation? That is also most important thing. What is the equation that you are seeking? So I now define a unit cell, suppose here. Now this is treated as mass weighted or density weighted element for which we can assign a single velocity, right? Instead of writing velocities for each individual molecules, you are no longer expected to know about the molecules. As far as this description is concerned, you don't know whether they are there. For you, this is your unit cell, which can have a velocity at any given time. So it is a function of position and time, right? Velocity, function of position and time. Given that this is a collisional system, you must know that the pressure and all these are fundamentally collisional concepts in thermodynamics, right? So it can have locally, these are field variables. These are variables in field that are changing as a function of time. Ultimately, the question you are interested in, how given set of quantities, which could be velocity, pressure or density or temperature, how these set of quantities vary in space and time. As soon as you have found a solution V, you have actually solved the problem. So the ultimately entire problem of astrophysical flows, friction disk and everything, whatever it is, however fancy it sounds, all you are looking for is a solution for V. Okay, that is one thing to keep in mind. That this is your solution. We don't know that. Yeah. So for this fluid element, you can write down 3 fundamental thermodynamic variables which may be related by an equation of the state, so only two independent equations or only two independent variables. For example, somebody must have written for you the ideal gas equation of state, E is equal to rho RT. So one equation, so one constraint is there. Out of three, only two remain independent. These are three components of velocity. So you require at least 5 equations to solve and close your system of equations. So now one should march ahead and try to find what is the equation that governs each of these quantities. How do we solve those? How does the density change as a function of time and space? Each one of these for a given fluid element, yeah, can be defined is already an assumption called local thermodynamic equilibrium. That you can define that I have a fluid element which has this pressure and density and temperature. This is a concept under local thermodynamics. So, why local? Because only locally you can say that this is the pressure and temperature, and it can vary in space and time. If there is in strict equilibrium, you will not have any currents or something, but we are interested in flows, right? We can of course have hydrostatic equilibrium in which we know the distributions of pressure and density in a static case, but how does it move as situation changes, force changes, velocity, there is flow and motion? How are these quantities changing? So clearly there is a need for some sort of a time derivative, let's call it symbolically time derivative of V, T rho T. Of course, this can be combined. So these are in total 3 plus 2 independent, 5 equations that are needed. Okay. How do you define now the time variable? Yeah. So you have done Lagrangian derivatives. Yeah. You have seen that. Yes. So then it is simple. You know that it is essentially you define a derivative as a fluid flows, right, along the path. That already requires a lot of assumption that you can define a path. Okay? So there is a lot of problems here. Okay? But we will come to those problems a little later. We may not even know the trajectory that it is taking. Trajectory of a particle, if you know, that is already a solution. We don't know the trajectory. But let's call it an imaginary trajectory that possibly is clear and known for an infinitesimal amount of time over an infinitesimal distance from a point A. Okay, suppose this is given. Okay, it is possible that the velocity is so rough that you cannot even connect the 2 points by a smooth curve. That may be a problem with turbulence already. Okay? We may not know. But over an infinitesimal time and infinitesimal distance between point A and B, which are separated by space-time distance delta x and delta t. So delta x here and delta t is a space-time distance between A and B. Okay, that's one way to say. There is a velocity v pointing in this direction at location A. This velocity is assigned to a fluid particle, okay, which has its own pressure, temperature, and density, which can vary along the path. Okay. This part can take an arbitrary trajectory or even an unknown trajectory, but let's go in the spirit of Taylor expansion and let's declare that the function that we are talking about, it's a field variable, like velocity, it's a field variable, it's a variable in the field. Yeah? Pressure is a field variable. So F could represent any of those variables, yeah? Or a component of the velocity. So it's any field variable which is defined at x, y, z, and t. And the underlying fundamental assumption here is that we can Taylor expand this function. That means the function is very big. It is not necessarily possible that you can always Taylor expand a function. But we are talking about those functions which are still smooth and well behaved, for which a function, the same function at the point B, which is separated by delta x, delta y, delta z in space and delta t in time, I can Taylor expand this point about the location of A. Right? So this you can do, right? It's nothing for one-dimensional problem. This becomes actually four-dimensional problem. In fact, it's called a 3D problem because time is considered a 0D problem. Time is 0 plus 3 space, so 4 in general, but it's called 3D problem. So when you say 3D, you are assuming time as 0. You are counting from 0. So if I have a function and I want to expand it about point x naught. Suppose it's a 1D problem. I want to know the behavior of function at location x, and I know the properties of the function at location x naught. Suppose, so you know that if these are very well-behaved functions, that means the derivatives exist. That is all one means. Then, by simply knowing the properties and all its derivatives of the function at this point, you can reconstruct the function at any other point. It's very powerful theorem in that sense, right? That I am interested in function at this point, but I don't know that. I only know the function at this point, but all its derivatives are known at this point. It's enough for you to reconstruct the function at any other point by Taylor expansion. So this is one way, which I will say a proper way to look at the Taylor series. That this function you want to reconstruct by knowing the function's behavior at this point. If it is a 1D problem, you can just say df by dx evaluate at x naught plus, one can write it more simply, f double dash at x naught. Sometimes people use this type of notation, f double dash x naught, to take second order derivative of x, f, and then evaluate it at x naught, plus an infinite series. If you're lucky, your series truncates at first or second order. As you see, if this quantity x minus x naught is very small, just to keep something in the head, suppose by small I mean 10 to the minus 1 even. And if this is delta x, I say, is of order 10 to minus 1, meaning I choose it to be small, such that delta x is of order 10 minus 1, then terms delta x square is of order 10 to minus 2, and delta x to the power n as 10 to the power minus n, right? That can be very, very small quantity and correction. So, if you make sure that the separation was infinitesimal, you can stop at the first order itself. Yeah? And you say that I declare that my fd is simply this, fa plus the derivatives of f at a, everything at a, everything evaluated at a. So now it's very simple. You take fb minus fa, divide by small delta t, and take the limit of delta t going to 0. Formally, how you define your derivatives. So you just say fb minus fa delta t, limit delta t going to 0. And given by nature we are looking at derivative as the material or fluid element flows along a streamline. Yeah, this you would call a streamline. Path trajectories of fluid elements and streamlines are two different things. That is also something that one should. Streamlines are extrapolations of a curve based on velocity at this point. Paths of trajectories are completely different things, which can be different depending on the nature of the velocity and the turbulence and the various other things. Streamline, over which we are defining this, is simply an imaginary concept. We are hoping that it works. Okay, so this quantity we call a material derivative or Lagrangian derivative, which simply tells you the variation of the as the fluid particle moves in space and time. Okay, if the steady problem, you know, the steady problem is when there is no explicit time variable. Yeah? Steady problems have no explicit time dependence, so your del t will go to 0. Yeah? Quite often we are interested in steady problems. That what happens in a steady state when things are not changing in time. Yeah? They are still changing, but they are not changing in time. Okay, I can have a flow like a current. Just imagine a wind blowing. If at any given location the speed of the wind direction it doesn't change, you call it a steady wind. Right? But the wind is blowing, right? And then the derivative. Just try to understand the meaning of this quantity v dot grad of f. If I say, what does it signify? This is some sort of a df for me. Yeah? What does it mean? V dot grad of F. If I just ask you that V dot grad of a quantity is 0, suppose I just declare in this room, how would you physically understand this statement? V dot grad is F is 0. What does it mean? Huh? What? No, speak louder.
Systems considering.
No. I'm going very slow today, so sorry for that. But tomorrow we'll shift gear. But today let's spend some time on just the very basic definitions of derivatives, fluids, and stuff like that, which is very essential before you can claim any understanding. You will hear a lot of things, which is what happens later, that people hear a lot of things, galaxy, ISF, and all that. They don't understand it. The reason is that there are gaps in these very basic definitions. So if there is anything unclear, this is the time to spend time. Later on, things are easy, actually. So what does it mean? V dot grad of F is 0.
This change because of the as the fluid particles due to the
So it's partly true, but not precise.
spatial change is 0.
No, special change is there. I'm not saying the gradient of the principle. I'm saying V dot gradient. If it's still a function of x, y, z, it can change. Huh? Not uniform. Uniform means it's an independent of position, right? That it is same here and here. Then I will write df by dx as 0, df by dy as 0, if it is uniform. I'm not saying that. I'm saying V dot grad of this. This is at the origin of your all Bernoulli's theorem and everything. But this is a route to see an appreciate Bernoulli's theorem later on. All it means is a directional derivative. I'm taking a derivative of a quantity, but along a given direction. So it's a directional derivative. So the quantity does not change along the direction of the fluid. It can change in other directions. Because there are all directions possible. Fluid is moving only along one of infinite possibilities. It so happens that along this direction the quantity does not change, but it's a very powerful thing. Yeah? So this is simply a directional derivative, and I can say that if it's a steady system, then streamlines and paths are same, it turns out. So along the streamline, if you know a streamline, along the streamline the quantity doesn't change. It's very powerful. So that means if I know a behavior of a particle, ultimately you want to know F, right? Whatever is there. So if I know the value of the F at this point, and if I know the streamline, and I am given this equation, I will know the value of F at all of everywhere, which can go from one end of the galaxy to another end of the galaxy. Yeah? So it's very powerful. Right. We will see some applications of this. Let's now formally define ideal fluid. I think I've said enough about it. But important to note that it does not exist in nature, but it's a very useful concept. Okay? In fact, it doesn't do justice by saying that it does not exist in nature, because most fluids in astrophysics, when we deal with, we actually treat as if it is an ideal fluid. We are not really bothered by the small viscosity. In many contexts, in many situations, viscosity is tend to be ignored in various textbooks at least. Yeah? It's unclear whether that's a useful thing to do. It may be small but very important. But it's a very useful concept. What is it? That it is non-dissipative. Yeah? Why is it non-dissipative? Because it does not exchange any energy with surroundings. So I can define a fluid element. Yeah? There are other fluid elements, right? That is how we are speaking. I push a fluid element here. That push is transferred to another fluid element. That is transferred to another fluid element, and that is how the waves are generated. In doing so, if it is an ideal fluid, there is no exchange between different fluid elements. Exchange meaning no mass exchange, no heat exchange, okay, between different fluids. So heat that is there in a given fluid element, as it is moving from one location to another, or a wind blowing from one end of the room to another end of the room, there is absolutely no heat exchange between the fluid element and the surrounding. So it retains its fluid. Heat.
Temperature, if it changes along the path.
Heat is different from temperature.
But it means some transfer has happened.
Within the ideal fluid, it is not possible. Within the ideal fluid definition, it is not allowed to exchange heat with its surrounding. It can expand, so temperature, it can cool and heat. It can become cooler and warmer, yeah, but adiabatically. All it means is that the process is adiabatic. There is no heat exchange, but it doesn't mean that you can't cool or get warm. Right? You can simply expand. Yeah? So that is what I mean. That if once you've defined your fluid element in terms of some bag here, that this is a bag. The reason I'm drawing it like that is because it is changing its shape all the time. Yeah? But it's not communicating with the surrounding in terms of any heat. So one of the boundary conditions, whenever the ideal fluid hits a wall, yeah, whenever there are solid boundaries that the fluid interacts with, the assumption is that the normal component, so if there is a wall here, the normal component, if I call it a normal component, that must vanish. Yeah? You can treat it as an elastic collision. If I hit it at a wall here, it will just emerge like that. Normal component vanishes. Okay? But it can slip at the wall. Slip, you understand? If it is an ideal fluid, right at the wall, it can slip because it cannot have any internal shear stress. There is no internal shear stress, internal stress in an ideal fluid. That is something we will come to when we introduce the concept of viscosity. That there are stresses, internal stresses in the fluid. Yeah? That's because of the some tensible nature of the pressure. But right now it's an isotropic pressure. There can be pressure, right, in the fluid. So the normal component of velocity vanishes on solid boundaries. So that's the boundary condition of ideal fluid. Okay. When we come to the viscous fluid, you will see that both normal and tangential component must vanish at the solid boundary. That means the relative velocity between the fluid and the solid boundaries must vanish. That is called no slip condition, no slip boundary conditions for the real fluid. Yeah. But here it is enough to say that it is a normal component that vanishes and it can slip at the boundary. Okay. Entropy of a particular fluid element, I said that this is basically like an adiabatic thing. T, if S is the entropy per unit mass, is 0 for a given fluid element. It's always 0. It doesn't change. It has an entropy, but it doesn't change. Whenever you say a change, you should always now keep in mind that change is both in space and time. So I'm writing material derivative of that you are supposed to expand as in time plus as that fluid element is carried along by the velocity. And if the velocity carries itself, that is the concept of self-advection. Suppose I write this mass or full derivative for the velocity field. After all, velocity is yet another field variable, right? At least something non-trivial here you can see is that if I were to expand this, you get the origin of all the known problems related to turbulence already here. That manifests in terms of self-advection. Self-advection is the hardest thing, and that is the origin of all turbulence. You see, all I did, I first defined my Lagrangian derivative here, and I simply applied it to the velocity field itself. You get a term which is non-linear. Yeah? It is no more linear. So v dot nabla v. That means change in velocity along the direction of velocity as it moves. Yeah. So you have to get it somewhat right in your head. It's not at all trivial. Okay. So don't analyze all the problems. And it's an unsolved problem, as you see, for centuries. So this is where the non-linear field origin of that self-advection. Okay.
If we define a unit set with such huge boundaries, how are we sure that it is the entire?
So, as far as this, you can, because at the wall, as I said, the normal component is 0. So, if suppose I take this fluid, all that was required for the unit cell is that it is freely allowed to deform, and it will deform if I hit a, if I come put it next to the solid ball, you will get a pancake-like unit cell. It will be like that. There is no problem, and it can actually slip right here. No problem with that. Because you want to.
That will also.
Yeah, because it's if I just think of two bag of balloons and let one balloon crush the other balloon. Yeah, the other balloon will give space to the other balloon. Right? Yeah, you can always deform it. So there is no restriction on the deformity of the unit cell. The identity is preserved by the smallness of the mean free path. That if there are some molecules, n number of molecules jump from one balloon to another, same on an average n number of molecules will also jump from this balloon to this balloon. So they can exchange, not in the ideal fluid, but in real fluid. Okay? Ideal fluid does not have any mass exchange. The fluid element will retain its identity strictly. In real fluid, you can have mass exchange between two different fluid elements. In fact, that is how that is called entrainment also. Entrainment. I can entrain, the fluid element can entrain mass from the debris, and that neighboring fluid element can have a different heat, and that can enter this fluid element, and that's how the heat exchange is possible in real fluids. That means the conductivity will become very important later on. Right now, viscosity and conductivity are important for an ideal fluid. But for real fluids, it is very much there. You can exchange heat, but no problem on the shape itself. It's all fluid, right? As soon as you draw an imaginary curve here, I can draw. Nothing stops me from drawing the imaginary curve just next to that.
Like at the boundary, if it gets deformed, doesn't mean that the identity of the adjacent fluid then will get
Nothing. Nothing. Yeah. There is no problem with it. It is very flexible. So this from here to here is obvious, so long as you know this. So can you show this? Yeah. So can you use your standard thermodynamics StatMech to show that the entropy, yeah, can be written in terms of log of P by rho to the gamma. Gamma is usual Cp by Cv. Yeah. Then only I can write that P by dt of entropy, which must be 0. I could also recast that equation in terms of pressure and density, because ultimately we want to write for pressure and density and stuff. Suppose I don't like the language of entropy. These are all variables one can eliminate in the interest of other variables. Right? I don't like density, so I'll write in terms of pressure. Yeah, you can always use some of these tricks. So suppose I want my equation to look in terms of pressure and density. So I can use this identity, the P by rho to the gamma, but then you must know explicitly that this is true. So that's an exercise. Show this. Let's move to now define, now to write the equation for density. What does density signify? Density in a volume is a mass. Yeah. Set of conservation laws will determine that you can't write more equations. You stop here because largely you are interested in things like energy stuff. That's only second order philosophy. You can go to higher order if you are interested. Nothing stops you because there are infinite hierarchical equations and concepts you can cook up. Yeah. But let's look at some traditional quantities like mass in a volume. So now this is not, now I'm not talking of a unit cell, I'm talking of some sort of a volume, yeah, which is bounded by a closed surface. And whenever I'm now writing velocity or something, it is assumed that it is for that unit cell. Now, the total mass in this volume can be written by integral of the density over that volume. Now, that rho can be a function of space amount. So, you have to be careful when you are integrating. Suppose I give you a density distribution of a star and ask you to determine mass, you have to actually know exact functional form of density as a function of r, say radius. Suppose that it only changes along radius, and then you integrate that function to get the total mass of the sun, for example. Right? So it need not be very simple integral; it can be very complicated. But in principle, this thing is correct. That the total mass within this bounded volume V is rho times dV, and my interest is to know how does the mass change in this volume. Yeah, there are winds from the star. Where generally, you are going to be interested in astrophysics, winds from the star and stuff like that. Mass has to be conserved. Means the only way the mass in this volume element will change is by having fluxes in or out of the boundaries. Right? You are not creating any mass here. There is no source or sink of mass in the volume. Yeah. The only way the mass can change in this volume is when you push. So suppose this is the n hat is the outward radial normal component defining an area element here. Suppose this is the small area element. The mass can change if there is a flow of matter, yeah, through this area element. So is this obvious that the flow of matter or a mass flux can be written as rho times v? This is obvious to you? If I take velocity small v, so just simplify the problem. You should be able to break down the problem in smallest piece possible. So if I give a velocity field here, passing through an area element delta s, yeah, delta s and velocity are both pointing in the same direction, suppose, yeah. So v dot delta s is positive. That means the mass is flowing out of the system. That means it must be then negative. You are losing mass from the volume, right? That's why the negative sign. So you see that if v and area element are pointing along the same direction, there is a mass flux outside that volume. If they are opposite, this whole thing becomes positive, and then there is mass inflow into the volume. That's why the minus is very important. Now, this is my area element. This was the velocity field. So, v times delta t is the distance. V times delta t is the distance traveled along direction, say x. If the mass was flowing at velocity v, in time delta t, it would have covered delta x. Total volume is then delta s delta x. Yeah. So you can work it out, right? So what do you get? Delta s delta v. Delta s delta x is anyway volume. So delta this capital volume, delta v delta t. Yeah. So now you can see the origin of v dot ds type thing coming here. Yeah. Take the time derivative on the other hand side because you are interested in the rate of change of that mass flow. So that is this dt here, which was here this delta t. Yeah. Total mass content in this was rho times delta. Yeah. Rho times delta v was the total mass. Yeah. So is it now obvious to you that rho times small v is the mass flux per unit volume? Yeah. So try to see. This is another exercise. We can then discuss why we are calling it a mass flux. Mass flux is matter that is moving out, flux of mass, which has to involve velocity because that gives you that cylinder. So it's all here. So you just work it out. Okay. So now this is an integral form of the equation. This is an integral form of the equation. I can make use of Stokes theorem. So this is a surface integral. I can convert it into the divergence of rho v, and the integral of rho dv can be combined to another volume integral. So we can get rid of this integral equation. This is more useful to understand physically what is going on in terms of mass fluxes and everything. But typically you just write a partial differential equation in terms of del rho by del t. That means the density can change only by divergences of mass flux. That's a conservative form of an equation. The density can change or any quantity can change. It need not be density. It will be the flux density. Yeah? So the quantity change is possible only by divergence or the fluxes of. Yeah?
Why did we not use the Lagrange derivative?
You can do that. See,
So in the first, the del by del.
yeah, because that is my volume is fixed here. No? I'm talking of a fixed volume here.
This is not the fluid.
This is not a fluid element. That's why I said the first thing. This is not a fluid element. Now, this is made of various fluid elements. I'm given, think of this as a sun. Sun is, entire sun is not a fluid element. So, from the sun, the only way I can now see that the mass of the sun will change, think of this as a sun, then it helps. It's an Eulerian problem, right? We are not interested in looking at as the sun moves, how the mass changes. No, mass is changing in an Eulerian manner. So it's so small this del t is called an Eulerian derivative, fixed in a space. Okay, capital d by dt is a Lagrangian derivative as you move along a flow. So the right thing to look at is an Eulerian derivative of a total mass enclosed in a volume. How does that change? Right? So then it's a relevant thing here. Now you can do Stokes theorem and you combine this and write this as del T of a density plus a divergence of the flux density of the same quantity. In this case, it is a mass flux. Yeah? This coming simply because of the cylinder type thing. You can see must be 0. Okay. Now I can of course combine because definitions are now very clear. So this is the continuity equation. Okay. So this is one of the most important equation, continuity equation. So if I'm given all these talks are very bad. Some of these del t plus divergence of rho v, I can open it as v dot grad rho plus rho divergence of v equals 0, right? Now this whole thing I can combine into t by d, t rho by d, right? Yeah. So total derivative of density is nothing but minus density times divergence of v. It's very interesting here that the entire idea of incompressibility can be written in terms of flow, velocity. Incompressibility is property that you can't compress a fluid, right? So density. But to ensure that, the velocity will ensure that. So divergence of v being 0 is already a statement on the incompressibility of it. Okay. Now the air in this room looks very gaseous and everything, right? What do you think air in this room is? Is it compressible or incompressible? There is a reason I'm asking this. It depends on the situation asked. The same fluid is definitely compressible because we are speaking. There is no sound in incompressible, right? But for most practical purposes, yeah. For example, speed at which we are moving, we are, yeah, and or something. Is this compressible or incompressible? So it turns out this is actually another long discussion. So just to bear in mind, and you read about it later, a good approximation is that whenever speeds involved in any medium, okay, are much smaller than the local sound speed, you treat that medium as an incompressible medium. So for that medium, while the sound speed is there, we can treat this sound speed as infinite and go into a regime that the medium in this room is compressible, incompressible. Sorry. Because the speeds involved. What is the sound speed in this medium? 330 meters per second. What are the typical speeds in this room? We are moving my hand or you're walking or running at what typical speeds? Maybe at the most a meter per second, 1 meter per second, less than that. Yeah. So the speeds involved in various discussions in the room and stuff is much smaller than the sound speed. Hence, for all practical purposes, the fluid can be treated as incompressible. All it means is that the perturbations that I'm making by moving my hand, okay, those are immediately washed out. Otherwise, by moving hand, you could form stars here. Think about it. Later on, we will also, I don't know if you'll have time to look up Jeans instability, for example. The instability that finally governs the collapse of gravitating objects lead to, say, formation of stars and stuff, Jeans stability. it's actually not so ridiculous that in certain regime, by just moving your hand, you could form a star. Okay. If the local sound speeds are very small, for example. Yeah. Okay. It so happens that whatever perturbations that are caused by our motion are washed out at the speed of sound, that for practical purposes, as we are walking, the perturbations that I'm causing in this room and in this air are washed out at the speed of sound, which are almost like a infinite speed for most practical purposes. 330 meters per second, any perturbation caused is washed out, right? So it's remarkable, and therefore, anything that you do for velocity in this room, you can actually just assume that divergence of V is zero. It's a very great simplification of the problem. Okay, that's why I'm bringing this. So instead of solving for whole density and this complicated equation, it's not a simple equation. All you have to assume is that divergence of V is zero for an incompressible medium, and just move ahead. Okay. Now let's look at the equation of motion. Equation of motion, this is all classical fluid, right? Equation of motion is what? Newton's law, second law of motion. Yeah. Acceleration should be equal to all the forces that are applied on a fluid element. Simple, right? So let's work out what are the forces possible. There are body forces and there are internal forces. Ideal fluid does not have a shear stress. There is no shear stress because there is no viscosity, but it has pressure inside. We know that if I apply much more pressure here and little pressure on this side, I can cause a wind. Right? There will be motion simply because of pressure. That you can somewhat feel at least. That if I push on air here, it will move ahead because I've just pushed it on this side. Right? So if there are pressure in the fluid, what is the force? So let's look at this unit cell. This is now an idealized unit cell. The concept is much more general. You can apply it to, again, you go to this infinitesimal area element and work out your pressure forces. But for the ease of discussion, you imagine a cube here. And on this surface, okay, if there is pressure P at this location of the fluid, so what is happening? There is a unit cell here, and because of pressure distribution in the surrounding medium, it is being pushed and knocked by neighboring fluid elements. The neighboring fluid is pushing on. As we are speaking, I'm also pushing the air here, right? So it's being pushed in certain direction. So if this is pushed here, depending on some pressure. This is pushed here from some direction. So what are all the forces on this unit parcel? If you work it out, that is your equation of motion, right? So if P is a pressure at this edge, the P times delta A pointing in this direction, Ex is a unit vector along x direction. Okay? So neighboring fluid, imaginary neighboring fluid here is pushing this unit cell in this direction. Imaginary neighboring fluid here is pushing this fluid element in this direction. So at least directions are clear, right? That you can do for all sides. That's why the arrows are drawn like that. Now, how much is the value of that push? What is the value of that push? So if P is a pressure, ultimately you have to work out what is the P and pressure distribution. I can ask a question, no? How is the pressure distributed from the ground level to a mountain level? Valid question, no? So clearly, if there is a high pressure here, low pressure here, somewhere there will be a push. It must be pushing the fluid. Maybe that is the reason that we have winds and circulations. Why there is wind after? You ask all these questions. All these questions can be addressed within the realm of this fluid dynamics. Okay. So if delta x is the separation between this edge and this edge, P times delta A is the total force exerted on this wall. Again, this is a Taylor expansion. Okay. Sorry for that. So again, if this is my one side and this is my another side, so let's put it like that. P is here, P as a function of x, and this is a location which is x plus delta x away here, right? So I can write P of x plus delta x as P of x plus delta x del P by del x, right? So write del because P is a function of x, y, z and t. Okay. Similarly, higher order terms which we ignore because now we are considering a very small fluid element. After all, it is by definition very small, right? So you get this. Now you simply add all these forces. Yeah, you take a vector sum of the forces on the unit cell, and you get this whole force acting along the x direction, right? We are typically interested in the per unit volume type quantity. Yeah. So del P by del X into delta V, because this delta A times delta X here, this is the volume of the unit parcel. So that's basically my whole force on a fluid element because of pressure distribution in the fluid. If, as you can see, if the pressure is uniform everywhere, there is no force coming from the pressure. Okay. That is a bad enough situation. Okay. You can generalize this whole unit cell type thing. Surrounding fluid exerts force on the surface of the parcel, that I can take a pressure, multiply by that area element, negative of that. Yeah. If n hat is a direction outward normal, the pressure force on a unit cell due to surrounding fluid has to be inward of that. So that's why the negative sign. Okay. That's one way to think. So of course I can generalize it and write radiate of P, again Stokes theorem. Yeah, and it becomes a volume integral. So surface force per unit volume. So it's a surface force per unit volume minus grade P. So remember, this is an ideal fluid. This is an isotropic pressure. Okay, that means if I consider the fluid, the pressure, isotropic pressure, exerts a force normal to an area always. Okay, there is no shear. There is no internal shear, but we will come to that shear later. So always whenever we are imagining a pressure in this room exerting a force on anything, it is always normal to the surface. The surface can be imagined. I can imagine the surface any which way. It's an isotropic pressure. So at any given surface, the pressure force is always perpendicular to the surface. Okay. No shear stress in ideal fluid. You can change the situation by having shear. That is later. So let's write down formally momentum conservation. We just looked at mass conservation, now we look at momentum conservation. You just apply Newton's second law of motion, you get again one of the most powerful equations of fluid dynamics. Okay. Before Navier in Stokes, this is an Euler equation. Later on, you will know about the Euler equation. Now acceleration, mass into acceleration, right? Or acceleration is force per unit mass, which is what? Rate of change of velocity itself, right? But that has to be taken, as I wrote before, in terms of moving fluid element, and you get self-advection. That is your left-hand side. Okay? You can also subject your unit cell to a body force. Body force is externally applied force. I can put the fluid, in a gravitational field on a rotating chamber, right? I can put water in some sort of a rotating thing. These are all idealizations of, say, rotating neutron stars. There are other body forces that can be applied and exerted on the unit cell. Okay, that forces also. So again, as you know Newton's law, this is your mass times acceleration. You add all the forces that are there. As simple as that, right? Vector sum of all the forces. We work out surface force due to pressure distribution. We can have a body force, which is say the gravity. Yeah. So the body force can be written down as minus rho times gradient phi. It's a general way of writing. That's a conservative body force, right? Yeah. Gradient of a potential leads to a conservative force, right? It's a conservative system. Yeah. So if you are confused about that at any point, you can see that if this is the Earth, yeah. If at any stage you're confused that this is a body force, why it is minus rho gravity. This is of course body force per unit volume. Okay, and if this G is pointing along minus Z direction, Z is pointing upward. That's a very typical. The reason I'm drawing this diagram is that next is a exercise for you to work out distribution of pressure in a hydrostatic equilibrium. How is pressure varying as a function of height in Earth's atmosphere? That is something as an exercise, but I think you have enough tools to work it out. Okay. So if gravity is pointing downward, right? Earth's gravity pointing downward, I can write minus g Ez. Yeah. So vector g, I can write as minus gradient of phi. Yeah. That is typically how you write. Phi is your gravitational potential. G is your acceleration due to gravity. Phi, I can write as simply g times z, where g, scalar g, is greater than 0. And that convince yourself that it satisfies that if I write phi is equal to gz, g is constant and greater than 0, you get minus GEZ, right? This is your total gravitational field equal to, or let's write it here, that vector G is minus GEZ. So within this convention, you can change the convention, but I'm saying this is my convention. I can write like this. In any case, this is acceleration due to gravity. I take, which is force per unit mass. If I want to write force per unit volume, I just have to multiply by density. Right? So if G is force per unit mass, right? And if I multiply by density, I get density, dimension of density is mass by volume, right? Mass cancels, you get force per unit volume. Okay? So that is what is written. Okay? So this is force, body force per unit volume. Okay? So now we have all the tools here. If I divide by density everything, this is like acceleration, which is force per unit mass. So I can write it. Gradient P was force per unit volume, right? Surface force per unit volume was grad P. If I divide it by rho, I get surface force per unit mass. So convince yourself that this is all fine. Okay? Force per unit mass, body force, I just remove this rho. So grad phi is force per unit mass. That's an acceleration. So you can write, some people like to write rho on this side, some people write like this. Either way it's fine, so long as your dimensions are all fine. This is okay. So this is a momentum balance for an ideal fluid. Okay? That rate of change of velocity, total rate of change of velocity is given by the surface forces, body forces, and any other additional forces that you subject your fluid to. Okay. In general, one writes equations in conservation form. What is the conservation form of an equation? Yeah? It's always written like that. Then there will be of the density of a quantity. It can be anything. Density can be just density. It can be momentum density. It can be energy density. It can be higher order densities. Yeah? You can construct much higher order densities. We stop at energy. Density of a quantity plus divergence of flux density of the same quantity is always 0. This is a statement written in terms of a conservation form. Okay. So every equation, including this one, you should be able to cast it in terms of conservation form. So that's an exercise. Write your momentum equation in terms of this. Now this will start to look a little technical, and tomorrow it will be much more technical. That you write the momentum density, like density of a quantity, right? So what is momentum density? Momentum per unit volume. Momentum is m times v. Per unit volume is mv by rho, mv by volume. This is rho times v, right? So rho times v is momentum density. Energy is, say, I could write mv square by 2 kinetic energy. Yeah. I want to write it per unit volume. That means the density of energy. Then it is rho u square. So you see that this is rho v square. Energy density. This is internal energy. There are not only, because this is a fluid has its own internal energy, right? Yeah. Internal energy, you've looked at second law of thermodynamics and everything, right? What do you write? TDS is equal to dU plus PdV and stuff. Yeah. But if I'm writing per unit mass, I can write specific volume is nothing but 1 by density, right? Yeah. Specific volume is 1 over rho. U is CV times T. This is what is CP, CV, these things you know, right? From your standard courses. So make sure that this is all clear to you. Yeah. So for example, can I ask why CP is always greater than CV for ideal fluid, perfect gas?
CP minus CV is equal to what?
No, why? Question is CP by CV, which you write as gamma, For monatomic gases, it is 5 by third. In this room, for example, it's a good enough approximation. Gamma is 5 third. What does it mean? Cp is 5 by third is larger than 1. Cp is larger than Cv. Why is Cp larger than Cv? Any thoughts?
Cv is del Q by del T, but for Cp there is an extra term rather than.
I can write an extra term. How do you make sure that the sign of that extra term is positive? Can be a negative term.
Sir, gamma is equal to 1 plus 2 by F.
It doesn't matter. I mean, I'm just asking here. I can write gamma in any which way. I'm just asking why Cp is larger than Cv.
Need to do extra work to hold on pressure.
Yes, some extent yes. Yeah. You want to basically, how are you measuring? These are properties of the medium. You want to raise the temperature of a medium by adding heat to it. You can do it at constant pressure and constant volume. It turns out that for constant pressure, you have to do actually extra work. Yeah. At constant volume, this term disappears. Yeah. Yeah. So you have to add more heat. What it effectively means is inefficient. Larger Cp is inefficient to raise the temperature. Okay, it's actually a reverse. Anyway, so think about all that. What is Cp, Cv, and all that means. Work it out equations like this, and you will use many of these things to write equations in a conservation form. Again, any quantity you choose, write the density of that quantity. Put that in a form which is divergence of the flux density. Convince yourself that this is a divergence here, right? I've ignored the body force, so you don't need to include it. You can include it. This is body force. So ignore that and just simply try to write that this equation is fine. Convince yourself that this del del xj is a divergence. Yeah. This will be useful because next when you introduce viscosity, it will all become too much tensorial in nature with all the shear and everything. So deriving the equations as conservation laws, because in just 3 lectures, deriving this will be long. This one we have anyway done, right? As you can see, if you want to start from here, all you will need is that you will require continuity equation. You combine continuity equation with momentum equation here. Combine the two and you will get a form like that. So it's not very difficult. The difficult part is energy equation. If you are really interested, then you look up Landau equations. Notice that here is internal energy U, which is Cv times T. Here it's enthalpy, which is U plus E by rho. You know it's enthalpy also? Yeah? So try to convince yourself why you are getting enthalpy here. Yeah? So these are all very fun derivations, so you should do it, but it takes time. Maybe we stop here. What happens after this? Is there a class now or? 11. Oh, so there is no break. It's a break time, right? Okay. So we'll meet tomorrow. I will go through quickly some applications. If you can, try to do some of these exercises, some thermodynamic simple exercises. Tomorrow there will be more exercise. Then maybe we can quickly do something fancier, but this is very basic. Any question?
In this thing, ds upon dt is 0. Sir, we know entropy is the parameter of disorder. Then, so why in fluid, motion of fluid, the particles are always changing with respect to time, but ds upon dt is 0?
No, it's an entropy of a specific fluid element. Yeah, you could say that the disorder of that fluid element is not changing. See, when you write that, you're writing in terms of inequality, right? You always write an inequality. That what do you write?
Yes.
ds. Yeah, ds is what? Greater than equal to dq by t. Something like that. So it can also remain equal. And as you can see already from here, that if dq is 0, ds is 0. The definition of ideal fluid is that there is no heat exchange, so dq is always 0. So ds cannot change. That is one way to see. But the fluid element is allowed to expand and contract, but it has to retain its entropy. So while it may, so that is why you see, you could think that the entropy of say hot air is larger because it has more kinetic energy and stuff like that. So if I have a small hole in the wall, you see the breeze coming through is suddenly cooler. That is an adiabatic expansion, right? So you can see that if I have to preserve my entropy, as it expands, I must pull it down. If you don't pull it down sufficiently fast, you will increase your entropy. Yeah? Because now you got now the molecule got larger room to cover. Right? Entropy, one thinks in terms of number of accessible microstates, right? Isn't it? So one would say that if the fluid parcel enhances or expands, now the molecules got much larger space to cover. Number of possible microstates must have gone up. Entropy must increase. So it's a valid point. But of course, as I say, this is an adiabatic expansion. So the temperature cools down. So particles are more still. So they really can't explode so much. Yeah.
Sir, when we speak, our sound is already compressing the medium. Then how can we treat it in compressed?
That's what I said, no? That the speed matters. The sound we could hear, first of all, because our ear is sensitive to that, and for those purposes, at those speeds, you spoke, I just heard, right? There's no lag. Almost we can treat it as instantaneous communication. Right? So at those speeds, the medium is compressible. The point is, any medium is both compressible and incompressible. It depends on the question you ask. If you are interested in questions like perturbations in this air as I walk, after all, it's a gaseous room, right? I am perturbing the medium as I'm moving my hand, doing others. Why is there nothing here or nothing is happening here? Because of all those rate perturbations. Even if you take measurement of say pressure here, just as I move, and you put a barometer and measure, you will not see any change. Yeah. These experiments are possible, people do it, and you see that there is no change. Why? Because all those changes that are happening due to motions at low speeds are being washed out. Mechanical equilibrium is reached instantly at the speed of sound. That's why we say that the fluid here is in mechanical equilibrium because the pressure balances out all these perturbations. So it washes out. But it is possible that it doesn't. It is not able to wash out over some large distances. If you consider distances that are very large, that your sound crossing time is large, yeah, compared to say the length scale is very large. This is all the Jeans length and criterion of Jeans length that you. If you could not wash out this perturbation over a scale which involved a certain mass, it will collapse and form a star. Because if I suddenly compressed a region, which I could do, I could have just clapped here and I compressed the region. Why I couldn't make it a self-gravitating object? Momentarily, there is some sort of a density enhancement. Yeah, all particles are gravitating. Yeah. So the gravity is always attractive. They should attract further. It should go undergo some sort of instability. It doesn't happen. Fine. So unless the perturbation involves at least length scales, it involves sound crossing time. So for all practical purposes, small distances, small speeds, the medium is pretty much even. Yeah, and yeah, if you have more questions or something, we can always come to. I'm still talking. Today, no break for this, but you can start with late.
I thought it is the Panjab.
No, now. Oh, there's one. Okay, so we stop it here. It's still recording.
There is from.
Huh?
Santosh.
Okay. So what do? I can't do any serious. Seems he's still recording. Maybe I stop.
Recording stopped.
So yeah, you please go for your break. Sorry that you were short.
We can start after 15 minutes.
Yeah.
So, or yeah. 15 minutes.
Yeah, no, I think we just kept talking.
So done.
Yeah, today. Right. So you all are very simple. We'll start after like that. Oh, we have to tell this online participants also. Hello, people. So we will start after at 11:15. Let's say speaking later. There is a stress. Pressure is stress. Isotropic pressure. Pressure is like a stress. It's just an isotropic. Isotropic stress is called pressure.
Then unstable is
Yeah. No shear. I said for ideal there is no shear stress. Shear stress is different. That is like the component like you're right maybe I'll do more like just shear stress. Shear is like something shear is change to something in a direction which is different from the direction of that something. So del VI by del XJ is the kind of the shear. The change in the ith component of velocity as you move in their component of the direction. If there is such a thing, then you call it a shear. But in ideal foot, there is no tension.
Change should be a norm.
Yes, exactly. Shear will always involve some sort of displacement because that element is then connected by the internal viscosity. That is quite difficult. True, definitely. But this is in other books that are very Jackson, tradition. It's a simplification that people take. That the loss in the electron's energy is much less compared to the loss because you are interested in radiation. And for the acceleration that for the electrons that are generated, you invoke secondary mechanisms to accelerate and supply them. So you always maintain that even if suppose your question is perfectly valid, that electron is generating, is moving energy in terms of radiation, electron should also slow it down. Eventually, it will slow it down so much that there will be no radiation. But you see radiation all the time. Right? Suppose I make an observation, I see radiation all the time. My assertion is that there must be secondary mechanisms that must be further accelerating the electron. So at any given time, there is always electrons available at that energy scale, and they will be radiating. Each time, it is a different electron that is radiating. It's not the same electron. That electron would have lost energy and gone out of that energy window. But other electron might have come into that energy window but be radiating. Yes. What? Yeah, you will boost the radiation. They will all, you will see the radiation as coming from a collection of charges, not a single charge. Of course, it is coming from a collection of charges. They may even build in different directions. Yes. So you look at from here or there, you will still see because there is always some species that are radiating. Then you must look for the radiation spectrum in the shape. If there is if you go to the relative spectrum, which is the pseudotronometer. Yeah, you know that as the electron is gyrating along the magnetic field line, it is emitting in a very small angle in a forward direction delta theta, very tiny angle. So if you look at the radiation in the direction which is not contained in the delta theta, you will not see a synchronous. It's a pointed emission in a given direction. But if you have a collection of charges, they can be emitting all over. You will see a collectivity here. Thanks, guys. Yeah.
Because there I didn't that radiation. It's very a problem. Yeah, this is very selection.